All right, ladies and gentlemen, today we're going to continue our discussion on ionization. Let's take a step back and look at another representation of the way that a strong or a weak acid, in the same manner a strong and a weak base, ionize. You know that if you have a strong acid, you start out with the acid molecules, and in a solution, all of the particles dissociate or break apart. So if you had 2 molar HA and it's a strong acid, you also have 2 molar hydrogen ions and 2 molar anions. However, if you have a weak acid or a weak base, it does not dissociate completely and it makes an equilibrium situation. So you start out with the weak acid or base molecules, and at equilibrium you have mostly molecules and a few ions. That would be represented here. You can calculate the percent dissociation or the percent ionization for an acid or a base. Let's take a moment to reflect that a calculation is not necessary for a strong acid or a base. Why?
Because it goes all the way.
Yeah. The answer for what the percent dissociation or ionization for a strong acid is 100%. I guess you could do some calculations, but not necessary. For anything that is weak, that would be the opposite of the strong, you can use this formula. The percent ionization of an acid is equal to the concentration, remember brackets denote molarity, the molarity of the hydrogen ion over the molarity of the acid that you started with. Because these are weak, we could do this with the rice table and determine how much of this is gone, but we don't. This is the starting concentration, and this would be the ending concentration. Okay, here it would be for a weak base. So in order to use this equation, you have to realize how things dissociate, how they break apart. So there's some rules on how they break apart. Let's look at exercise 2, do a little practicing, and then we will come back. Hydrochloric acid dissociates completely, so HCl breaks apart in that fashion. The rules here state that they dissociate 1 proton at a time. 1 proton at a time. Acetic acid has 1 labile proton. What does labile mean? One that can be broken apart, one that ionizes. A labile proton is one that ionizes. Acetic acid has 1 labile proton. That means that this one will dissociate, these will not, because they're part of the polyatomic ion. So acetic acid loses its proton. It's a weak acid, so it's an equilibrium situation. If it has a double-headed arrow, it should bring you into mind of all the equilibrium work we've done so far, and you could write an equilibrium expression for this, couldn't you? Yes, and you will be. All right, now this is an odd-looking acid, isn't it? By whose model is this an acid? Arrhenius or Bronsted-Lowry? Bronsted-Lowry. Let's dissociate it. NH4 plus. Is it strong or weak? Weak. Because it certainly is not a no sober class clown in Hawaii. It will lose its proton, and what's left over is ammonia. Phosphoric acid is triprotic. What does that mean? It has 3 labile proteins. 3. I'm hungry, and if I say protein again, 3 labile protons. They dissociate one at a time. One at a time. Let's look at what that looks like. Initially, this occurs. Then, the second hydrogen ion is cleaved off. And lastly, the remaining proton is gone. So this step, you can think of it as happening in steps. This happens, and then subsequent to that, this happens, and subsequent to that, that happens. Is it really like that? No, but for our purposes, you can think of it that way. I would like you to think about, in these steps, how Le Chatelier's principle is involved. When this first step happens, this occurs. When this second step happens, there is a complication due to Le Chatelier's principle. What is that complication?
Oh, there's an increase in products.
There is an increase in products. Where does that increase in products come from here? From this proton that's running around in the solution from the first dissociation. It would be like adding an H plus in Le Chatelier's expression, which would shift equilibrium which way? To the left. So, which do you think dissociates more, step 1 or step 2?
Step 1.
Step 1 by far. And then when you get to step 3, you have the proton from this step and the few protons from this step pushing equilibrium even further to the left. And very, very few of these lose that last proton. Do you understand? Okay. All right. Back up here, now that we've talked about ionization, we've talked about what an ionization equation looks like, let's talk about equilibrium expressions, not to get these confused. An equilibrium expression for an acid dissolved in water would be just like we've done so far. So if we had a weak acid, and we know that this is an aqueous solution, we know that it breaks apart like this. I've left the water out of it because water isn't a player in the equilibrium expression. So the equilibrium expression here is Ka would be equal to the hydrogen ion concentration times, in this case, the acetate ion concentration over the concentration of the acetic acid. You can write a Ka value for all weak acids. It is only appropriate for a weak acid. A strong acid goes all the way to completion. You don't need to know, if you know the starting concentration of a strong acid, you know the concentration of the H plus and the anion, yes? So a Ka value is only for a weak acid. Now, weak acids have Ka values, lots and lots of weak acids, lots and lots of Ka values. The bigger the Ka value, the stronger the acid. What does that mean? The bigger the Ka value, the more it dissociates. Yep, the more it dissociates. So if you had a dissociation percentage that was 25% for one acid, and a dissociation percent for a second acid that was 15%, you could say the first acid was stronger because it ionizes more, yes? And you would suspect that the first acid has a Ka value bigger than the second one.
Could there potentially be a problem on making when they say the Ka is 25, the Ka is 15, which one's a stronger acid?
Yes, absolutely. I think you'll see that in questions I ask you as well, yes.
So when we look at the phosphoric acid, we would say that the Ka of H3PO4 is stronger than the Ka of the transport.
Absolutely. In multiprotic acids, that means it has more than one proton, you can write a Ka value for each step. This one would be Ka1, this one would be Ka2, and this one would be Ka3. Ka1 would be much larger than Ka3. I think we're ready to move on. On the second page, I included a bunch of, and this comes right from your book, for face-to-face use only. I included a number of weak acids, their formulas, and their ionization reaction with Ka values, because sometimes they're tricky. Now, I'm not going to go through the math to do this, but I want you to know this. If you have a weak acid, let's say my favorite, acetic acid, and it dissociates in this fashion, if you have an initial concentration of 0.25 molar, and you figure out the percent dissociation based on that, and then you have the same acid at a lower concentration, you will find that this one will dissociate more than this one will. All conditions being equal, and the explanation for that would be due to Le Chatelier's principle.
So the bonding will dissociate?
Dissociates more. The percent dissociation would be greater here than it would be there, which is kind of counterintuitive.
Well, isn't it because there's less concentration right there?
Yes.
It's easier. The bonds are easier.
Well, no, it all has to do with Le Chatelier's principle.
So since there's less, it shifts more to the right.
Because there's more shifts to the left. And then I have more acids in their ionization constants. Okay. Yesterday we spent a lot of time making sure that we did not confuse strength of an acid with concentration. A strong acid is one in which equilibrium lies far to the right. It has such a large value of Ka that it is not published. There is no Ka value for a strong acid. A strong acid produces a weak conjugate base. Right? Yes. A strong acid produces a weak conjugate base. I'm going to write a Bronsted-Lowry a Bronsted-Lowry equation here. If this is the acid, what's it going to do? What?
H 3O5.
It's going to, Bronsted-Lowry, it's going to donate its proton
And become the conjugate base.
and become the conjugate base. And the water acting as the base will receive it. So here we have the acid, this is the base, this would be the conjugate,
So,
and this is the conjugate acid.
so the conjugate.
This is a weak conjugate base. It is very unlikely to pull this proton away and go that way. Understand what I'm talking about? If this is strong, this is weak. A weak acid here's our acid, here's our base, conjugate acid. A weak acid produces a strong conjugate base. It is more likely to pull this proton off and go this way. Does that make sense? Absolutely. You know, this is a one-way direction. This has the possibility to go both ways.
Did you say yesterday that we might have trouble with determining if it's like a strong acid, if we can't remember them? Can you just look at the arrow and if it's double sided?
Yeah, as long as somebody helps you out there. I'm guessing you don't have the equation. And somebody will just say hydrochloric acid dissociates.
On the AP test?
Yeah, and it would be up to you to know completely. Strong acids, we're talking about no silver class plants in Idaho. All right, ladies and gentlemen, I have here a bunch of information that is pertinent to you that will allow you to qualitatively determine the relative strengths of acids. And I'm just going to talk about it in a nanosecond. It's up to you to read it, understand it, and be able to use the information. Okay, if we're talking about a binary acid, that would be two elements. The more electronegative the bond between the proton and the anion, the more acidic the bond. The stronger the bond between the X and the H and the anion, the weaker the acid. We saw that yesterday. Binary acid strength increases across a period and increases down a column. We see the bond energy for the bond energy for a acid made from a halogen. In talking about oxyacids, here is the trend. And I would just like you to read the rest. Likewise, this chart, and I want to get to strong bases. And you know what the nice thing about this whole thing is the acids and bases react the same way. A strong base completely dissociates, a weak base does not. A strong base does not have a Kb value, a weak base does, because it's an equilibrium situation. And there are very few, like there are very few strong acids, there are very few strong bases. For our purposes and the purposes of AP, a strong base is any base that contains a group 1 cation. A group 1 cation. Okay. You can write a dissociation reaction for a strong or a weak base. You can write an equilibrium expression for a strong and a weak base, and they are as you would predict they would be. Now the tricky part comes in writing the dissociation expression for some of these weak bases. Yesterday we talked about amine groups. and how that was a clue that that would be a base. Let's look at ethylamine. If somebody gives you that and asks you to write the dissociation expression for it, that would be kind of difficult for you. Let's put some water in it and write a Bronsted-Lowry equation. When you don't know what to do, attempt to write a Bronsted-Lowry equation and it'll point you in the right direction. So here is the formula for ethylamine. We're adding the water. You're to decide which one acts as a base and which one acts as the water. We see that it has the clue of an amine group, so we know this is going to be the base. This is going to be the acid. So this will dissociate like that.
So the OH is the conjugate acid.
This would be the base, and then this would be the conjugate acid. This would be the acid, so this is the conjugate base. Huh? No. No, see, it's not. That's,
I'm in
I
the
need-
conjugate base.
You always find the conjugate, the best rule of thumb I can tell you is look for the conjugate based on what happened across the equation. All right, and the biggest fail point for kids in writing the Bronsted-Lowry equation is leaving off the charges. If you leave the charges off, they're wrong. Okay, moving on. Yesterday I talked about water and I said that it could act as an acid or a base. What is the term for a substance that can act as an acid or a base? That was so yesterday. Just gonna wait for somebody to find their notes and look that up.
Amphotoroid.
Yeah, there we go, thank you. Amphoteric, it's amphoteric and act as an acid or a base. So that gives rise to this situation. Water can act as a Bronsted-Lowry acid and a Bronsted-Lowry base. Here it is, right here. If this were the acid and this were the base, what would this be?
Conjugate.
And the, all right. Are we good there? Now.
So that just happens with like water in general, where it's just focused
Right.
on the cloud?
Now, this, you could write an equilibrium expression for this, couldn't you? There it is. It does not have the water because water is a pure liquid. So the equilibrium expression governing this process happening is Kw, which is the specific equilibrium constant for water. It'd be great if you stayed away. Equilibrium expression for water is equal to the concentration of the proton or hydronium ion times the hydroxide ion. Like all equilibrium constants, this doesn't change with concentration. What changes it? Temperature. At room temperature, which we say is 25 degrees C, the value of the Kw is 1 times 10 to the negative 14th. That will be an important number to you.
Is that for all of them?
For Kw, that governs only this. That does not mean Ka and Kb. I think that's what you're asking.
Yeah.
Is this standard?
Now, is it true that Ka and Kb are constant all the time at room temperature? Yep. Does it change when the temperature changes? Yes. I've never seen anyone ask you to figure out Ka or Kb when temperature changes, but I guess they could. Right, this is called the autoionization of water. Based on the value of K, which side does equilibrium favor? The left or the right? By far. So if you were to look at a particle diagram of a beaker of water, you would see lots of water molecules and very few ions, yes? Yes. Okay. Change the temperature. Okay. Now, if I were going to write a rice table for this, and I had this happening, for every molecule of this that dissociated, one of these would be formed and one of these would be formed, correct? That gives rise to a number of scenarios. If at equilibrium, my hydroxide and my hydrogen ion concentration are equal, I would have a neutral solution. That would be pH of 7, when we're talking about pH tomorrow. If my hydroxide concentration was greater than my proton concentration, it would be basic. And if the opposite was true, it would be acidic. Based on that, you can use this equation. The ionization constant of water, which is constant, is equal to the Ka value times the Kb value. Where did they come from?
So is this one not, oh, it's only water, so.
No, it's because all of these acid-base things are happening in water. If you knew the Ka of acetic acid, you could calculate the Kb of acetic acid because it's happening, I'll be right here, with water, okay?
What if it's a strong acid?
If it's a strong acid or a strong base, we're not calculating any Ka or Kb value, and I have one. Yes.
Isn't KW constant only at room temperature?
Yes. So this would require some temperature changes. Is that what you're asking?
No, like KW for it to change, it would require
The temperature change, we're going to change the temperature in just a minute.
So, but they would like say like, when the KW.
That you have to define the temperature at which your reaction is occurring. And if you were asked to determine Ka or Kb, they would have to give you the Kw value at every temperature. And just so happens, here is the Kw at different temperatures. Yay. Doesn't change all that much, huh? All right. Okay, let us move to this, and I'm going to, in terms of simplicity, because we're new at this, we're going to do this. H2O does this. I've added the water in there, and it's difficult for you to see this. So change this equation. It says here that at 60 degrees C, the value of Kw is 1 times 10 to the negative 13. What is the Kw at 25 degrees C?
1.0.
Is 1 times 10 to the negative 14. It says predict whether this is an exothermic or endothermic reaction. If this reaction were exothermic, where would heat be in this equation? It would be in the product side. If this is endothermic, heat would be on the left side. What is the equilibrium expression that we would use to talk about the autoionization of water? Kw is equal to, and what they're basically asking is predict which side the heat will go based on how Kw changed. We did this in general equilibrium by looking to see, is the numerator going to get bigger or is the denominator going to get bigger? In this case, we just have the numerator, yes? So, let's look at these two values. Which is a bigger number? 1 times 10 to the negative 13 or 1 times 10 to the negative 14? The first one is bigger. So this is a big number, this is the small number. So So when they heated up the water, the equilibrium constant got,
Bigger. Smaller?
no, it got bigger.
It got bigger.
It got bigger. Okay. Yep, that's the problem here. It got bigger. The equilibrium constant got bigger. If you have a big equilibrium constant, is there more of this or more of that? More of this. So far, so good, yes? Heated it up and more product was made.
So,
Why did it shift?
because the heat was.
Because the equilibrium was disturbed. Now that you know some shift occurred, now you have to figure out if heat was here or heat was here. If you heated it up
It's just.
and heat was here, which way would it shift? To the right. And if it shifted to the right, there would be more of that, correct? Now, if heat were here and you heated it up, it would shift to the, and this quantity would get, and KW would get smaller. So this must be what type of reaction? Endothermic. All right, now it says calculate the H plus and OH concentration in a neutral solution at 60 degrees C. Okay. I'm gonna use this space up here. This would be a rice kind of thing, wouldn't it? Water does this.